Should be good. All right, folks. I hope you had a good weekend. Let's pick up where we left off. I brought the slides from previous class. Yeah, okay, the last one. So, we kind of wrapped. We were done with rotation kinematics, and I told you pretty much that's all. Whatever I needed you to know. Also put some practice problem related to rotation kinematics on Moodle. You will see it on the rotation kinematics section, problems with solutions. So you can also use those problems to practice. Once we're done with motion kinematics, which I'm hoping will be done in this week, I'm thinking about having midterm next Thursday, but let's finalize that by the end of this weekend. We'll see how things go and how fast we move forward. But once we're done with motion kinematics, we're going to have our midterm, right? The exam. Uh, Basically, first and only exam, and then for the second part, I'll give you a project and also another final project. So we'll have two projects, but this is going to be the only exam that we'll have for the course. And again, as I said, once we're done with motion kinematics, we're going to have the exam. And I'm hoping that it would be next Thursday. But let's see how things go today and this Thursday. I just have to be able to finish motion kinematics. I think it will be done this week. Um, so for now, set the time for midterm. It's obviously subject to change, but set it next, not this Thursday, Thursday after, 25th. We might push it back to Monday, but we'll see how things work. All right, we'll talk about it more on Thursday this week. All right. I'll give you more details about the exam. For now, just let's keep that in mind as a tentative date. All right, motion kinematics. That's basically That's the last thing we talked about in the class. That I said, well, we talked about rotation. In rotation kinematics, we only had a rigid body that was only allowed to be rotated or to rotate around X, Y, Z axes, global coordinate frame axes. Now, when we come to motion kinematics, obviously, when you have a rigid body in three-dimensional space, that body can rotate around three axes or can also translate. Now, to just be able to describe the motion or motion kinematics, which includes both rotation and translation, we just added one piece to what we had from before. We said, well, if R represents the position of a point, and position of a point, you can think about it as a point on a rigid body. If lowercase r represent the position of a point in global coordinate frame, that is equal to the multiplication of rotation matrix, which we talked about those rotation matrices, rotation on X, Y, or Z global coordinate frames. I said that's all we need to know. In global coordinate frame, multiplied by the position of that point in local coordinate frame. Right? That position could be the initial position or final position because local coordinate frame is basically attached to a rigid body. Sometimes you'll see they also represent this RG. It's the same as RGB. You'll see that notation too, maybe in your textbook. RG is the same as RGB. You'll see that too, meaning that this rotation matrix is basically rotating local coordinate frame B in global coordinate frame G. All right, that's superscript and subscript and superscript on the upper left side. So basically, it makes it a little probably easier to represent because in your mind you can think about this as RGB multiplied by RB, and that will give you RG. I don't know, maybe some kind of a mental process that canceling out B's. So we go back to global coordinate frame. But you will see that the story is the same. You'll see that they represent it as R using RBG, meaning the rotation of local frame or body frame in global coordinate frame. It's the same thing. And we said what we had from before, plus dg, d being the translation vector, wherever the origin of local coordinate frame goes during the motion, or wherever we are at the end of the motion. That d is basically a vector. Remember, everything here, rg is a vector. I usually, I don't put these when I in robotics because everything is a vector. But r is a vector, this is a vector, and this is a vector, and this is a 3x3 matrix. Right? So these are all vectors. In three-dimensional space, they have three components, x, y, z. And remember, this d right here, let me just add it here, d is translation in, or let's say final position, maybe this is better, final position in global coordinate frame, right? Wherever you are at the end was d, and d should be represented in global coordinate frame. That's what that g does in top left, saying that this d position vector is in, or displacement, or call it displacement maybe, in global coordinate frame. All right. All right. Since we start from the origin, the final position and displacement should be the same. All right. So let's take a look at a couple of examples. That's pretty much all into this. Very straightforward. Just playing around with, make sure that you do the right multiplications, represent the vectors correctly. The rest of it is basically just math. Right. So let's take a look at a couple of examples to start with simple ones and then look at a couple of more interesting ones. So let's start with something basic. Let's say you have a body coordinate frame. So we have a body coordinate frame, and remember we just said body and coordinate frame and local coordinate frame are pretty much the same in our terminology. So a body coordinate frame B, and let's represent that O, X, Y, Z, which is attached, which is, let's put it this way, which is originally, attached is not, which is originally coincided or coincident with global coordinate frame G being O, X, Y, Z, comma, it rotates 45 degrees about x-axis, and then and translates. Basically, when we say this coordinate frame rotates and translates, it means the body that this coordinate frame is attached to rotates and translates. Right? Translates to, I'll represent that with 3, 5, 7 transpose, meaning that's vertical, if you want to think about that. Now, the question is find the global position of point R in local coordinate frame X, Y, Z. General point in global in local coordinate frame. You can write it as X naught, Y naught, and Z naught, so it doesn't get mixed up with X, Y, Z coordinate frame. All right, pretty straightforward. This is more like an example to show how the process works. So R in local coordinate frame, well, we are given as X naught, Y naught, Z naught, some values. D, right, is given 3, 5, 7. And we also have the rotation. We are told that it rotates around x-axis 45 degrees. So rotation matrix, we talked about this when we were talking about rotation kinematics. Well, 1, 0, 0, 0, 0. And then this one is cosine 45. Let me write cosine. Remember, I told you I'm going to use C and S for cosine and sine. But I guess in this case, I can just write it. Cosine 45 degrees minus sine. This is minus sine. Then this becomes sine 45 degrees, cosine 45 degrees. All right. So pretty straightforward. R G is equal to R x 45 degrees. Right? Rotation matrix multiplied by the position of point in local coordinate frame plus dg. That's what we're going to do. I'm going to say, well, if the final position we call it x naught, y naught, z naught, wherever it is that we're trying to find, is multiplied by my rotation matrix 0, 0, 0, 0, cosine 45 minus sine 45, sine 45, and cosine 45, right? Degrees, obviously. Multiply by x naught, y naught, z naught plus 3, 5, 7. You do this, you'll get, well, let's do the multiplication. RG, or even better, let me just write it right in front of it. Can I fit it here? You're gonna hate me for that, probably. X naught plus 3, the first one is straightforward. Then you'll get y naught cosine 45 degrees minus y naught sine 45 degrees, like that one, plus 5. I'm doing everything in one step. So this is a 3 by 3 matrix. This is a 3 by 1 vector. This is a 3 by 1 vector. I do the multiplication here and then add the values by, so the output of this is a 3 by 1 vector, right? And then add the corresponding values with whatever value I have in x, y, or z, corresponding value from this vector there. So just putting everything together. Third line, third component would be y naught sine 45 degrees plus z naught cosine 45 degrees plus 7. There you go, fit it there. If you do that final calculation, you'll get x naught as well. 45 is just a square root of 2 over 2. This was going to give you x naught plus 3. Y naught is going to give you square root of 2 over 2 multiplied by y naught minus, I made a mistake there. This shouldn't be y naught, right? This is 0, and this is z naught. This becomes z naught. Z naught, 45 degrees. You'll probably see that. Z naught plus 5, and then z coordinate in global coordinate frame would be square root of 2 over 2. Then over there you have y naught plus z naught plus 7. So this is pretty much a demonstration of how the process works. The same story as before. You were doing the first part previously when we were dealing with this part, you were doing it before, right? R times rotation matrix multiplied by the position of the pointing local coordinate frame, right? The only thing added is the translation at the end, 3, 5, 7. So we'll just add that value to whatever the rotation was to get the coordinate in global coordinate frame, a global position, right? So knowing that where the point is in local coordinate frame, you can find where the point is in global coordinate frame at the end of this motion kinematics, which includes a 45 degrees rotation over the x-axis and a translation to 3, 5, 7. All right. Hopefully that makes sense. So this is the general process. I'll go over a couple more examples. I think most of them are pretty straightforward. But by saying that, I'm not stopping you from asking questions, obviously, because it might seem straightforward to me, but might be very confusing. So just let me know if these examples I'm going over. I think I can go over at least another example in this, or maybe 2 more examples on this before we get into homogeneous transformation. How can we put everything together in just one matrix? All right. So I'm gonna wait a few seconds if there's any question on this one. Also, if any comment, I made any mistake, let me know. All right. So this one, yeah, I think straightforward. We have a point P. Actually, I think just to give you a better sense, I'm just going to bring out the picture that we were using at the beginning when we started talking about this topic. Now, we have a point P right there, right? We are given the coordinate of this point in local coordinate frame or body frame. Then we're told it's rotated, and we're given the information. We want to find out what is the final position of point P. Very similar to what we did before, with just numbers this time instead of parameters. Right, so the point P is, or better to say, at R in local coordinate frame P is 0.1 I, 0.3 J plus 0.3 K in a body frame B. The body frame B, actually, let's continue this. Rotates 45 degrees. Actually, this one is 50 degrees. You see a lot of 45 and 9 degrees when we're dealing with robotic arms, but rotates 50 degrees about z-axis. Translate -1 along x-axis, along x, 0.5 along y.
I have a question.
Go ahead, Lucas.
So the variable is labeled R when it's from an origin to a point, and it's labeled D when it's from an origin to an origin.
Wait, a D is, yes, exactly. So R is the position vector for where the point is. Now, if it's RB is the position vector for representing where the point is in body frame or local coordinate frame. If it's RG is position vector representing where the point is in global coordinate frame. Now, DG is going from origin to origin, as you said. Origin of the global coordinate frame to the origin of local coordinate frame when we have a translation.
Right, okay, thank you.
At this course, at least a good portion of it is more about notations, and just get comfortable with notations. Have a good definition of notation. Once you know the notations and definitions and what they are representing, the rest is really not that That I think complicated. Usually mistakes happen when we have misunderstanding somewhere. What these parameters are, what are they represent, what do they represent. So 0.5 along y and 0.2 along, well, z-axis, along z-axis. Now find the final position of point P. P in global coordinate frame. So here is what's happening. Just this is important. These are important to understand because of later on when we start talking about other topics. So here is what's happening. Remember what we were doing. This is X, this is Y, and this is Z at the beginning. Right? Local coordinate frame or body frame. That's where it is at the beginning. We are going to have 3 rotations. Remember, we always go with rotation first when we want to know, when we want to imagine how things work. Don't do translation and rotation. Do rotation first, deal with all the rotations. In this case, we only have one. We'll see later on we have multiple rotations. So you do all the rotations first, and then do the translation. So here we have a rotation 50 degrees about z-axis. Right? You do your rotation about z-axis 50 degrees. Like it's z, so it's going to be this direction, positive. Just point that out that these are the positive directions. If you have x, I don't know if I mentioned that, y, and z. If this is x, if this is x, this is y, and this is z, here are your rotation. This is positive rotation about x-axis in positive direction, rotation about y-axis in positive direction, rotation about z-axis in positive direction. Right? So when you see positive, it means it's rotating in this direction. It's basically a right-hand rule. Use your thumb to represent the axis. Your 4 fingers, when you're trying to make a fist, represent the direction of the rotation. These are the positive directions. If I didn't mention that, just keep that somewhere. Remember that. Pretty much follows, as I said, right-hand rule. So it rotates 50 degrees about z-axis, and then once you rotate it, when you, after rotation, let's say it's x, y, z, then you're going to have a translation. You go from here to here. So you do all the rotations first, and then make the translation. All right, so in this case, let me clean up here. Makes it messy. In this case, well, we know what is the local, the coordinate frame for the position of the point. We are directly given that value. We know the rotation. It's rotation around z-axis for 50 degrees. And we know d. Right? D is actually given by its components. You say -1 along x-axis, 0.5 along y-axis, and 0.2 along z-axis. So dg is basically is -1, 0.5, 0.2, or transpose. And oh, that's good enough. So r g, global coordinate frame for point P at the end of this rotation, is basically a rotation around z-axis for 50 degrees multiplied by r in global coordinate frame point P plus dg. We just replace the values. R z in 50 degrees, well, it's rotation around z-axis, 0, 0, 1, 0, 0. That'll give you cosine 50 degrees, a minus sine 50 degrees, sine 50 degrees, cosine 50 degrees. And this is the rotation matrix about z for 50 degrees. Then you have R, position is 0.1, 0.3, 0.3, and plus the translation, which is -1, 0.5, 0.2. You do this math, you'll get, remember, you have a 3 by 3 matrix. Do this multiplication. I'm not going to do it for this one. 3 by 3 multiplied by 3 by 1 vector. This gives you a 3 by 1 vector. And then you add up the corresponding elements of these 3 by 1 vectors and this 3 by 1 vectors. Whatever you get there, add it up, add it by -1. Whatever you get here, add it by 0.5, and whatever you get there, add it by 0.2. If you do that, you're going to end up having, for reference, -1.165, 0.769, and then 0.5. This would be the position of point B in global coordinate from after this motion. Right? So in this case, it was just an example with numbers. Again, remember, always do the rotation first and do the translation in your mind to get the right answer. All right, so let's look at something a little, maybe not more complicated, but at least closer to what we're going to do in robotics a little bit. Then we'll get to even things that are more closer. So we have.
Can you go back for a quick second, Professor?
Sure. If I can figure that. All right. Yeah.
Okay, you can go back. I'm good.
Just get comfortable with operations, matrix operations, matrix vector operations. You use your calculator. Just get comfortable doing it on your calculator. You do it manually. Just be comfortable with doing it manually to get the right numbers, right? And you'll see you're going to end up having 4 by 1 multiplication matrix vectors. Just be comfortable with that. Practice that one. That one thing that might take time during your exam would be just doing these multiplications and these operations. All right. So the next one, let's say we have a very simple arm, I would say, about the arm. Not that much of an arm in this case, I guess. So simple one. Now in this case, we are basically following point P. Point P is going from where it is right now, called P1, to the final position P2. Right? It's just going from, I can think about A, where we are, B, where we will be at the end of this motion. Now, write the problem statement this way. The position vector, of, or there's no D. Position vector of point P1 at the tip of an arm is RP1 in local coordinate frame. Components are 1,350, 0, 900 transpose millimeters. The arm rotates about rotates 60 degrees about Z axis, and then elongates by D is equal to 720.2 I, but this is D. The final position, a final, let's put this global. Oh, I have to make this question. Right? Find the final position of, how many more times I have to write this to get it right, but hopefully that's the last time. Global position of the tip of arm, tip of arm. So we start from here. Maybe I can do a better job there. Things don't get mixed. This is P1 where it is, and then this one is P2 where we're going to be, right? P2. All right, so well, we need to find a couple of things. We need to find the rotation matrix, which is basically mentioned kind of directly 60 degrees about z-axis. We need to find where the point P1 is at the beginning. That's also given, 1350, 900 millimeters, that's XYZ components. We need to find D, the translation or the position, final position of the origin of local coordinate frame in global coordinate frame. Right? So here is the general equation that we have. We know RG, you can write it as, you want to add a point to it, RP2G is equal to RG Z in 60 degrees, RB P1 or P2, doesn't matter, they're the same. Local coordinate frame is attached to that, plus DG. Right, that was the general expression. Now RZ60, we already know that. That's given, I would say. This we know. Position of point, tip of the arm in local coordinate frame also is known. Now, in order to find this one, which we don't know, we also need to know this. Now, what is DG? Can someone tell me what DG is?
Is that the elongation of the arm?
Right, so elongation of the arm is D, right? This one is D. But pay attention that this D is given in local coordinate frame. Right? It said it's 720.2 I, lowercase I, which is the unit vector for along x-axis of local coordinate frame. Now, what we want is we want this position, the position of the origin of the local coordinate frame, we want that in global coordinate frame. Here is where this point is. This, you can think about this as lowercase o and this as uppercase O, right? Small o and large O. So to find this DG, we have to find where we are, where the origin of local coordinate frame is in global coordinate frame. So how do I find that? Right. I know what D is. I know where the where it's located, but it's given in local coordinate frame, the original local coordinate frame. If this was O at the beginning of the motion, at the beginning we had O and O. Right? They're on top of each other. Now after the motion, it gets there, and this translation D is given in original where the local coordinate frame was at the beginning. It's in I, like lowercase I.
Is there some type of geometry that we need to do?
Yeah.
Is there a triangle in here?
Yeah, the right direction.
Where?
Uh, right direction. So yeah, so we just look at the geometry pretty much, right? If you look at the right triangle there, uh, let's see if I can draw it. Let's say we're looking it from the top. That's how I draw. It's supposed to be an eye looking from the top. I don't know. The best I can do. So let's say this is xy, right? This is x, this is y. Just draw this so nobody gets lost there. So this is y, and this
Would
is
it be 720.2 cosine 60?
cosine 60 would be x component, right? Look this, and then you get y component by sine 60, right?
Yeah.
Hopefully that's what you're following. Yeah. So that's exactly what I'm getting, right? Exactly. So this is going to be your d in local coordinate frame. It's given. And we know this angle is 60 degrees. So your component, the components of this vector, if you want to think about that, position of this point, the origin of local coordinate frame after translation, would be, let me write it this way, would be D, which is 720.2, right? Sine, cosine, well, actually, let's get it right. Cosine 60 degrees, the I component. 720.2 sine 60 degrees. And the Z component is just 0 because it's in the an XY plane. So we'll just keep it as 0. That's what your D becomes. If you don't see it, you can just let me add it here. So these are the components, right? This is DG in Y direction, and this is DG in X direction. And DG in X direction is D cosine 60 degrees, and DG in Y direction is D sine 60 degrees. So you go from your, this was your local coordinate frame. Right? This is your local coordinate frame at the end. We care about where the origin is. That D is supposed to represent the position of the origin after the motion is done. It gives you a better view, hopefully, that way. This is X, and this is Y. I'm looking from the top. So once you get your D in global coordinate frame, then the rest is pretty much, again, plugging in the values. Then this becomes RP2G is equal to, well, translation around Z, about Z 60 degrees, this becomes cosine 60 degrees minus sine 60 degrees 0, sine 60 degrees, cosine 60 degrees 0, 0, 0, 1. This is rotation about Z axis, right? And then you have a position of point P1, right? 1350, 0, 900, plus now you know the components, right? The first, this one, I'll just write it the way they are. 720.2 cosine 60 degrees, 720.2 sine 60 degrees, and 0. And the same story. A 3x1 matrix, a 3x1 vector, another 3x1 vector. You do this multiplication right here, you get a 3x1 vector. Then add the corresponding values with the other 3x1 vector. So you'll get your position P2 in global coordinate frame after this motion. So that'll give you, I'll give you the numbers: 1035.1, 1792.8, and then 900 millimeters. This is what you get after the rotation happens. All right, so just keep in mind that the equation is simple, But you have to pay attention and make sure that everything is represented correctly. Like the position is represented in local coordinate frame at the beginning or at the end. Local coordinate frame, they're the same as long as your frame is attached. Since your frame is attached to the rigid body, as a result, it's not. The initial and final position of the point as part of the rigid body in your local or body frame are going to be the same. Rotation matrix presented correctly, and D. D has to be represented in global coordinate frame. D being where your final position, the final position of your local coordinate frame in global coordinate frame. All right. Now, you can also have multiple rotations, right, which is very common. Right? You can have one rotation, let's say, about z-axis, another rotation about y-axis, and then a translation. If you have multiple rotations, you do what you were doing before for multiple rotations or successive rotations when you were just talking about rotation kinematics. Nothing changes there. That R matrix that you use for rotation, that basically is going to be a matrix that is going to be an R total, which is it can be found by multiplying the rotation matrices related to, or rotation matrices representing those rotations that your rigid body is going through, right? So just one quick example on that one. All right, let's go with this example. Let's say we move the body coordinate frame B to DG for the final position for -3, 7 transpose, this way, vertical position. Find R P in global coordinate frame if the local position of the point is RPB 732 transpose after frame G rotates 45 degrees about x-axis and 45 degrees about y-axis. Right. So we have two rotations. We know where the position of the point is in body frame, local coordinate frame. We have two rotations, and we know the translation of the origin. Right. All right. So the only thing changed here from before is that now we have two rotations. Now, since we have two rotations, the general formula is the same. The general equation that you were using R in global coordinate frame is R B plus DG. The general procedure is the same. Now, the only thing that changed here is that this R right there now is not just one R. We have to find it since it's a successive rotation. We have first 45-degree rotation about X and then another 45-degree about Y-axis. So to find that, hopefully you remember that I said when we are dealing with successive rotations, we start from the last rotation and move to the first. What I'm trying to say is that now here R you can think of it as R total, is we start from the last one, RY 45 degrees, multiplied by RX 45 degrees. Right? The last one is 45 degrees about Y, and then the one before that is 45 degrees about X. Or you can think about that, you go from this way. If I had another rotation, then that would have been like the first one. Always you start from the last one, multiply it in that order. So you can find RG, right? It's by multiplying those two matrices, we know these rotation matrices, right? We talked about them when we were talking about rotation kinematics, right? 45 degrees is going to be cosine 45 degrees 0. I obviously cannot fit this there, so let me not torture you from the beginning. I'll just move here. RG would be, I don't know if I made it better.
I have a question.
Go ahead, Lucas.
In the problem statement, you say after frame G rotates 45 degrees about x-axis and 45 degrees about y-axis. Are you rotating the global coordinate frame?
Yeah, maybe that's confusing. Let's just go with after frame B. Right, good point. End of the day, you'll see later on that doesn't matter, but let's stick with terminology. Right? Okay, thank you for pointing that out. The after frame B rotates 45 degrees.
Oh, okay.
Now it's correct. Yeah, that was confusing. All right. So we have R in global coordinate frame as look like GL. Multiplication of these two rotation matrices, right? This is 45 around y-axis, so cosine 45 degrees, 0 sine 45 degrees, and 0, 1, 0, then becomes minus sine 45 degrees, 0 cosine 45 degrees. And then this multiplied by was x, so this is 1, 0, 0, 0, 0. Then this becomes cosine 45 degrees minus sine 45 degrees, sine 45 degrees, and cosine 45 degrees, right? You do this multiplication, you'll get RG as also 3 by 3 matrix by a 3 by 3 matrix. Well, do a little bit of, so the first element becomes cosine 45, 0, 0. Let me just write it. So it becomes cosine, oh, not my fault. This becomes cosine 45 degrees. Then the second one becomes 0, 0, sine 45 degrees squared. I'll put this squared here. The third one would be 0, 0, and then sine 45 degrees, cosine 45 degrees. Second row, 0, 0, 0, so it becomes 0. Third row, second row, second element, 0, cosine 45 degrees. And then the final element, 0, minus sine 45 degrees. Last row, minus sine 45 degrees. Multiply this one, 0, 0, and sine 45, cosine 45, sine 45, cosine 45, and the final element 0, 0, cosine 45 degrees squared. You can plug in the numbers. It's just basically the rest is just calculating the sine and cosine of 45 degrees. Now, once you have that, the rest is pretty straightforward, right? We have RG is equal to R, that you found it from there, multiplied by RB, which is given as 7, 3, 2, right? Plus D, which is 4, minus 3, 7. You add this up, do the multiplication there. So this is a 3 by 3 matrix. This is a 3 by 1 vector plus a 3 by 1 vector. You do that, you'll get R, position of point P in global coordinate frame. I can use P here. At P, I usually put it. I don't put it. You just, you know, we're following point P. That'll give you 11.449 minus 2.293 and 4.551. That becomes the position of this point. So when you have successive rotations, the story is the same. You just make sure that you follow the right order when you're dealing with your rotations, all right? Hopefully that makes sense. All right. So what is the next step? All right, you'll say, oh, we're comfortable now. We can do rotation and we can do translation. So we should be able to actually look into anything pretty much in three-dimensional space. As long as we get our coordinate system right, we get our point representations in the right coordinate system, we should be fine. We should be able to trace any point in three-dimensional space. And remember, when we say global and local, you will see later on, we can use, I'll talk about compound transformation, meaning that you have multiple frames. So you just follow the same procedure. We'll talk about it later on. Maybe this week or probably next week. If you go with this pace, you might end up postponing the midterm. What next? Now, the next step would be, this is good. Now, the problem is when, as I said, when we have multiple transformation, we call it. Multiple rotation, you have multiple rotation, one translation, another multiple rotation, another translation, another multiple position. So if you have multiple of these, this process is not very efficient. Because for every time, for every, let's say you have one global, another local, and you have to do this process once, some translation and then rotation. Then you go from that one to the next one, and we're talking about multi-body systems. So we are not going to have only one global and one rigid body. We're going to have multiple bodies connected to each other. So we're going to end up having multiple frames attached to each one and treating in each step, treating the first one as global and second one as local. Now, what happens is that for that type of situation, when you have multiple, as they call it, multiple, what's the term for it? I skipped my mind. Multiple transformation. Let's go with this way. We'll see that later. This is not efficient because you have to do it every time. You remember when we were doing rotation kinematics, we said, well, like the one here, we said when we have successive rotations, we don't do R equals to position global frame equals to rotation matrix multiplied by position vector in local, and then do the one for the next one and do one for the next one. What we do is that we just find the final or total rotation matrix by multiplying these rotation matrices, and then we use this equation only once, right here. And we only use it once. Once we find the R, the rest is just, doesn't matter how many rotations you have. Now, we want a similar procedure for rotation and translation or general motion. Instead of doing this process every time we have a translation, right? So we have one rotation, translation, another rotation, translation. Instead of using or doing this multiple times every time for each step, we want something similar to successive rotations, right? If we have successive translations, we want something that we can find the final one matrix for all these rotations and translations, and then use this equation only once, or at least basically do the multiplication with the position local coordinate frame at the beginning to find the position at global coordinate frame at the end. Right? Now, to do that, we have to kind of get rid of this plus dg there and incorporate that into a matrix. And that's where homogeneous transformation comes into play. So that goes under homogeneous transformation. Let me